Hello, stat students. Welcome back for section 8.4. We're still hypothesis testing. We're going to use proportions. Remember, we're talking about p's and p-hats now. So over here on this right-hand side, I've got our symbols to talk about. We talked about these when we did proportions, when we did our confidence intervals. So p-hat, remember, is our sample proportion. The hat tells us it's a sample. If I don't give you the sample proportion or percentage, you know that it's X, the number of items with that characteristic, over N, the sample size. P is the population proportion. So no hat is population, hat is sample. We know that P and Q are complements of each other. So if P was the probability of success, whatever we're looking for, Q is the probability of failure. And we know that Q is 1 minus P. N, sample size, right? We've got that. And degree of freedom is, oh, I forgot to write that, N minus 1. So when we're talking about a population, or when we're talking about a proportion, population proportions or samples, we're working within that binomial distribution because either it happens or it doesn't. Either it's a yes or a no. There's two possible outcomes. So our two outcomes, so it's either a P or a Q, right? It's either a success or a failure. So remember, our probability of success does not change from trial to trial. In the real world, it's a little less common to talk about trials, but we'd be looking for some characteristics, some statistics, some fact. The number of people who have high blood pressure. You either do or you do not. Remember, back from whenever this was, it was ages ago, I think, we talked about how when we are dealing with a binomial distribution, our mu is equal to n times p. So mu doesn't come from just some number like how we've done in the past. We're going to do a calculation or be given that. Our sigma, our population standard deviation, is the square root of n times p times q. We've done these calculations before. And remember, we have to do that quick little check that n times p is greater than 5 or equal to, and n times q is also greater than or equal to 5. So our mu is greater than 5. And here is our z. Remember, we've done this formula. This is actually step, 3, computing our test statistic. I'll jot that down. This is step 3. Z is equal to p hat minus p all over the giant square root of p times q over n. This is where the calculator gets fun. Here's how we calculate our z. Since I'm telling you that our test statistic is z, I'm hoping that you're already knowing that we're going to use our z table for our critical values. So just putting that out there, it tells you if you know what to look for. And I thought, well, we probably don't need to rewrite all the steps of hypothesis testing, but they're exactly the same. So step 1, we're going to do our hypotheses and state our claim, all the same stuff that we've done before. We can also do these, we can do these exactly the same way. So let's see, it says, sugary diets. A dietitian claims that 60% of people avoid sugar in their diets. The dietitian randomly selected 200 people and found that 128 people stated that they did avoid sugar. At the alpha equals 0.05 level, is there enough evidence to reject the dietitian's claim? Use the traditional method. Hopefully that traditional method comment there makes you recognize that you can do the p-value. So let's do a couple things on the side. I always like to identify everything. So it looks to me like our p is right here, right? P is here. That's our population proportion. If a dietitian randomly selected 200 people, hello, here's our sample size. 128 people stated that they are avoiding sugar in their diet. Well, we have to do a calculation for p-hat. 128 people out of 200 are avoiding sugar. I believe that's going to be something like a 0.64 when we divide it out. So we know our p-hat. If our P is 60%, of course, we know that our Q would be equal to 40%. Turn your percentages into decimals. I think that's everything we need to know. So let's start by stating our null and alternative hypotheses. So our null hypothesis, we go to our P, we go to our mu, we go to our population number. So I'm going to say instead of mu equals, I'm going to say P equals 60%. Right? That's the only thing that changed. We're dealing with percentages and our proportions. Let's see. What does the dietitian claim? The dietitian claims that 60% of people avoid sugar. It doesn't say more than or less than, so we're just going to make this a two-tailed, not equal to 60%. So if we were looking at this, here's our 60% in the middle. We think that it could be on the lower or the higher end. So when we go to find our critical value at alpha equals 0.05, right, this is two-tailed, so I have to do alpha over 2, 0.025. I jump into my z table and I look for 0.025. I go to the closest one, and my critical value is going to be 1.96. If you did if you did 0.025, you would have gotten a negative 1.96, right? But since it's two-tailed, we know that it has to be positive and negative. So you just look to see which side. That's why that little visual is often helpful to knowing what sign should be on your critical value. All right, so step 3 is still computing the test statistic. So this one's a little bit different, right? Our our z is equal to, let me look at my last page. It says it's equal to p hat minus p. Well, we calculated our p hat at 0.64 minus our p is 0.6, 60%. That's all going to be over a giant square root of p times q over n. So p was 0.60 times 0.40 for our q, all over our n. There were 200 people involved in this. Figure out your calculator. This is a big deal. Make sure that when you calculate, hit pause and make sure you get a 1.15 for that calculation. It is positive. So if I'm going to use my visual here to help me out, if my critical values are negative and positive 1.96, my test statistic comes in right about here at 1.15. Are you going to reject or not reject the null hypothesis? It's in the non-reject region, right? It's not in those two ends where we think it could fall, so we are going to not reject H sub O. So if we don't, oh, I forgot to write this down. The claim was H sub O, right? So if we don't reject H sub O, and that was our claim, we can say something like there is not enough evidence to reject the claim that 60% of people avoid sugar. There is. Remember, the only way that we can definitely know if we should reject or not is to use the whole population. So all we can say at this point is there's not enough evidence to reject that claim that 60% avoid sugar in their diets, blah, blah, blah. That summary, again, is important because it sums up everything that we've just done. It sums up what the researcher thought and how everything goes. All right, so there is our traditional method. Feels the same. The only thing different is how we compute our test statistic. Everything else is the same. So let's pop on over here to example 8.10, exercising to reduce stress. A magazine states that 14% of men say they use exercise to reduce stress. Use alpha equals 0.02. Our random sample of 100 men was selected and 12 said that they do exercise to relieve stress. Use the p-value method to test the claim. Is it reasonable to generalize the results to all American adults? So let's see, 14% of men is what we're saying is the p. We know our alpha is 0.02. A random sample, n, of 100 men was selected. 12 say they exercise to reduce stress. So here's our p-hat calculation. 12 exercise out of 100. That's going to be a nice easy peasy 0.12. So let's start by doing our hypotheses. So remember, it's not mu, it's p is equal to, well, our p is, they're saying 0.14. And so is this a right or a left-tailed test? It doesn't tell us if it's more or less, so we're just going to go with a two-tailed 0.14. What is our claim in this particular case? The survey states nobody else is disputing that. So our claim is 14%. So again, for you visual people, here's our p equals 14%. We're wondering if a significant amount more or less than 14% exercise. So let's compute our test statistic. So this one's interesting, right? Because this is that using our answer from our test statistics. So we've got ourselves a z equals p hat minus p, so 0.12 minus 0.14, all over a giant square root of p times q. Well, we know q, right, has to be 0.86. Check my math on that. All divided by n, which would be 100. So do a quick math problem. Make sure that you also get a negative 0.58. So according to our sample, it's just over a half a standard deviation smaller than the mean. So now we're going to find our p-value. So this is where we actually go to the t-table, and we find our z-value if we've got a negative 0.58. So you go to the outside and work your way to the area. Remember, p-values are areas. So find area. So when I do negative 0.5 and then go across to the 8, I got an area of 0.2810. So let's use our sense here. So alpha was 0.02, right? So if alpha is 0.02, that means I'm splitting that between these two ends. So 0.2810 on the negative side. If I were to color that in, 0.2810 would probably be like way out here, right? That goes into the non-rejection. My area for my p is a lot larger than my area for my alpha, which means I am not going to reject. Do not reject. And then we would go ahead and I'm finding the last example. I skipped my summarize, but I don't want to drag this on forever. So we are not going to reject our claim, which is H sub O, so we would write our summary statement from that. I know I went quick through this section, but I feel like it's very similar. You have to refresh your memories on P's and Q's and just get that Z test statistic, but the steps are all the same. So hopefully you know what to expect, what to find next. Get yourself organized with what formula and what section. That is it for section 8.4. Thanks for hanging around.